Welcome everybody. Let's talk about the ideal gas law and STP. We need to begin by reviewing what we learned earlier this year. So we talked about the gas law variables, pressure, volume, temperature, and number of particles. And we also talked about how those were related to one another. So if you recall from the beginning of the school year, as the volume got larger, the pressure went down for our gas. And so graphically, we had a picture that looked like this. That is an inverse relationship, if you recall. And so we can mathematically say that the pressure is proportional to 1 over the volume. So as you look over here on the left, I have pressure is proportional to 1 over volume. And that little fishy symbol in the middle, that's my proportional symbol. So those are proportional to one another. We also saw that the pressure depended on the temperature, and as the temperature increased, the pressure increased. And as long as we're working with our Kelvin temperature, we have a nice direct relationship here. And so pressure is proportional to temperature. Lastly, we looked to see how the number of particles impacted the pressure. And as you recall, as the number of particles increased, the pressure increased. And so again, I have a direct relationship where pressure is directly proportional to the number of particles. And we work with these relationships with our iffy tables. Our goal today is to put all of these relationships together into a mathematical expression that will allow me to look at one gas, not changing, but at a gas at one moment in time. So if I combine these relationships, I have that pressure will be proportional to the number of particles and the temperature. Those will be in the numerator over the volume. And again, this is a proportionality. I want an equation. And so what we're going to do is we're going to add a proportionality constant. And so the pressure for a gas is equal to R times N times T over V, where R is what's called our ideal gas constant. And this is just a number. It never changes. That's why it's a constant. And this number is 0.0821 liters times atmospheres over mole Kelvin. Okay, let's take a quick look at this. This number, 0.0821, that's what you put in your calculator for R. The liters, atmospheres, mole Kelvin, these are just the units on that gas constant. So they don't change the number in any way, but they do determine what the units have to be for your pressure. Your pressure is going to have to be in atmospheres. For your temperature, that has to be in Kelvin. Well, that's always true. Kelvin temperature always has to be used for gas law problems. Your volume has to be in liters, and your number of particles has to be in moles. So while those units don't change the number you put in your calculator, they do define what units you have to use for the rest of the problem. So this is the ideal gas law. We typically write it without the denominator as PV equals nRT. Again, R is this ideal gas constant. And this is a really nice equation to use. If I know 3 of the 4 gas variables, because I always know R, I can find the missing value. So I can talk about one gas at one moment in time and figure out whatever piece of information I don't have. Let's work with this. I have 2 problems on this page. The first one says a gas occupies 16.4 liters at 25 degrees Celsius, 1.3 atmospheres. How many moles are there? The first thing I want you to do is to recognize that you're going to need an ideal gas equation. How you'll know that is you'll have one gas, one moment in time. Nothing's changing. You're just saying, here's a gas, tell me about it. That's when you know you're using your ideal gas equation. The second thing I want you to do is I want you to look at your units. The units in the problem have to match the units in your ideal gas equation, in your ideal gas constant. So the volume has to be in liters. It is. The temperature has to be in Kelvin. It's not. So the first thing we're going to do is do this conversion. And so remember to go from degrees Celsius to Kelvin, you add 273, which makes this 298 Kelvin. And then my pressure is in atmospheres. That's the correct unit. We're good to go. So from here, you're going to plug your numbers into the ideal gas equation. Now you have a choice. If you're comfortable manipulating the ideal gas equation symbolically, you can rearrange it to solve for the variable that you want. In this case, we're looking for moles, so that's N. and then plug your numbers in, or if you're less comfortable working symbolically, you can just plug your numbers into the ideal gas equation and solve it like you would any other problem. So we're going to do the latter. We're just going to plug our numbers in here. So our ideal gas equation is PV equals nRT. The pressure is 1.3 atmospheres. The volume is 16.4 liters. We don't know N, that's what we're solving for. R is this ideal gas equation, ideal gas constant. And then T is our temperature. To solve for N, I need to divide both sides of this equation by 0.0821 and by 298. And so when I do that, I find that I have 0.87 moles. I get 2 sig figs here because 1.3 atmospheres had 2 significant figures, so that will define my significant figures. A second example of this is down below. I've got 0.640 moles of a gas. It occupies 11.4 liters at 16 degrees Celsius. What's the pressure? Again, one gas, one moment in time. We're using the ideal gas equation. Then we need to check our units. I've got moles, that's good. I've got liters, that's good. I've got degrees Celsius, not good. So we're going to convert 16 degrees Celsius to 289 Kelvin. At that point in time, we can use our ideal gas equation. In this case, I don't know P, so that's what I'm going to solve for. My volume is 11.4 liters. N is 0.640 moles. R is that 0.0821. And then its units, and the temperature is 289 Kelvin. When I solve for pressure, I'll need to divide both sides of this equation by 11.4, and I get 1.33 atmospheres for my pressure. Here I get 3 significant figures because in the equation, when I was using it, I had 3 significant figures. The temperature does have 3 significant figures because when we added 16 to the 273, the last shared decimal place was the ones place, so I do have 3 sig figs here. One other thing I need you to recognize is a shorthand, and this is STP. STP stands for standard temperature and pressure. It corresponds to 1 atmosphere of pressure, that's the standard pressure, and 0 degrees Celsius or 273 Kelvin, that's the same temperature, but that is your standard temperature. When people work with STP, they often just think standard pressure. The T stands for temperature, standard, temperature, and pressure. And this is just a shorthand. It's just a shortcut for writing a problem. We don't actually change the math. We just have to remember that STP tells us both a temperature and a pressure, so we know those values. For example, what's the volume of 2.44 moles of hydrogen gas at STP? 2.44 moles, that's the right unit for our number of particles. STP tells me that the temperature is 273 Kelvin and the pressure is 1 atmosphere. This means, since I've got one gas at one moment in time, I can plug in my different values. My pressure is 1 atmosphere. I can solve for the volume since the question was what is the volume. I know the moles. I know the value for R because you always know the value for R. It is a constant. And I know the value for temperature. And so solving that equation, I get 54.7 liters. So in summary, the ideal gas law is a composite of all of the different gas relationships we had talked about earlier this year, and it allows us to answer for one gas at one moment in time, what's the value of the missing variable? So you're going to be plugging numbers into the equation PV equals nRT, where R is your ideal gas constant, and because it has units of liters, atmospheres per mole Kelvin, those are the units you have to use for all the other values in your equation, because within any equation, all your units must match. Lastly, STP is a shorthand and it stands for standard temperature and pressure, and that is 1 atmosphere and 0 degrees Celsius, or in Kelvin, 273 Kelvin.